Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, Oscillators and Amplifiers. This module deals with the amplifiers, single stage amplifier, small signal analysis of common emitter amplifier and introduction to multi-stage amplifier we are going to discuss today. In the single stage amplifier, in common emitter configuration, when you see the circuit diagram, this is the input terminal, that is the base terminal is the input terminal and the collector terminal is the output and emitter is the common terminal. Since this is the emitter configuration, emitter is common to both the input junction as well as the output junction. Here the signal is given through the capacitor C1 and there is a power supply VBB through the resistance RB, and here again this power supply is VCC for the output port through the resistance RC, and output is taken, output of the transistor is given as the input to the next stage of the amplifier through the capacitance also. So, across these two terminals you can get the output of this particular circuit, and we know that the input is forward biased and the output is reverse biased here, and the input signal, if you give an alternating voltage as the input signal to this common emitter circuit, how will be the output? What is the equation for the output? So, this is the single power supply, this is the dual power supply here. VBB is given for the input junction and VCC is given for the output junction. This is the circuit with the dual power supply, and this is the same circuit with the single power supply here. The signal is given through the capacitance C to the base of the transistor, and across the collector we are taking the output V0, and the supply is given to the base as well as to the collectors. From the same power supply we are giving the we are biasing the input side as well as the output junction of the transistor here, and this emitter terminal is a common terminal for both the input junction as well as the output junction. So, now consider that the signal is given, alternating signal, voltage signal is given to the input terminal, that is base terminal of the transistor, and you are getting the output but which is out of phase with the input signal by 180 degree. So, what is the equation for this output voltage V0? V0 is that output voltage taken across the collector and the ground. This can be written as this voltage VCC minus this voltage. The supply voltage VCC is given to the collector terminal through the resistance RC. So, the voltage at this point, that is, this is the total voltage VCC, from this point to ground is VCC minus the voltage drop across this resistance RC will be the output voltage now. So, VCC minus ICRC is equal to V out, and V out is VCE, that is the collector emitter voltage, voltage across the collector, and emitter is the output voltage. So, instead of V out you can V0, we can write it as VCE is equal to VCC minus ICRC, and when you look at this equation also, VCE is equal to VCC minus ICRC. This VCC is always constant because this is the supply we are giving to the collector terminal. So, this is the biasing supply we are giving to the collector terminal and also the base terminal. So, this VCC cannot be changed once it is fixed. So, this is a constant value, and according to the variation in the collector voltage, you are getting the output like this. You are getting the phase shift as 180 degree between the output and in the input. So, if the input voltage is positive half cycle, the the base current will be increased. If this is positive, if this is positively increasing, this base current is also increased, and for this common emitter beta is considerably high. So, according to the beta, that is the current amplification factor, this IC is also increased. This IC is increased, this is constant, and what is the output voltage, that is the voltage across this collector and emitter, VC is equal to VCC minus ICRC. Suppose this is fixed as 10 volts or 5 volts, if this IC is increased heavily, then you will be getting the output in the negative side, right. So, this is fixed and this is increasing as the base current increased. So, the output voltage across the collector emitter terminal will be in negative side. So, you are getting 180 degree out of phase with the input, right. So, only in the common emitter configuration we will be having the phase shift as 180 degree between the output and the input. This is the input voltage Vi with respect to the time, and this is the output voltage V naught with respect to the time. We know that how the phase shift has been arrived between input and output, and since it is an amplifier circuit, it gets amplified. The value is increased, the voltage is increased, and the phase shift is 180 degree between the input and the output. This is again a common emitter amplifier with voltage divider bias. Bias is a concept of giving supply to the transistor, whatever it may be. Bias is the concept of giving supply. Forward bias, reverse bias, in the sense, the literal meaning of bias, you can say that partiality, right. So, in the same way, if you give the input junction a forward bias and the output junction reverse bias, what does it mean? The positive terminal of the transistor, that is P type of the P terminal of the transistor is connected to the positive terminal of the supply, then it is a forward bias. If it is forward bias, then current flow is very, very high, and the P type to the positive terminal and N material to the negative terminal. If it is so, then it is a forward bias, and reverse bias is P type of the transistor is connected to the negative terminal of the supply, and N type of the transistor is connected to the positive terminal of the supply, then this is the reverse bias. In the reverse bias, we know that the current flow is very, very low, and for the transistor connected in a combination to produce a better amplification, then it has the for input junction must be forward biased and the output junction must be reverse biased. And in this biasing techniques, there are a lot of methods. One is the important biasing technique is the voltage divider bias, and other biases are also there, the self bias and collector bias is there. And this is now we are going to see only the voltage divider bias circuit, and why this circuit is called as voltage divider bias is only this VCC is the supply which is biasing the transistor. Now it is like a food for the human being. Once the supply is given, then only the circuit, the transistor will work, otherwise it will not work, right. It will work as an amplifier or oscillator, whatever the connection is given. If you give the supply, then only it will work, and this supply is different from this signal. This is the signal, and this is VCC is the supply and V in is the signal. Signal is, it can be in millivolts or in nanovolts. This signal needs to be amplified, so it is given in the input terminal of the transistor, and you are getting an output as the higher in magnitude than the input signal. So, this is the signal. This signal has to be processed through the transistor. The signal is also voltage, but there is a drastic difference between these two voltages. This VCC is given for the transistor for making the transistor to work. So, this is supply, or you can say this is bias, and this voltage is divided through these two resistors R1 and R2. We all know that these resistors are the potential dividers or voltage dividers, you can say like that. So, this R1 and R2, this combination of R1 and R2 will give you the voltage divider bias for this transistor circuit, for this transistor. And remaining the collector terminal has the load resistance which is connected in between collector and the supply voltage, and this RE is the emitter resistance which is connected between emitter and the ground, and the input signal is given through the capacitance and output is taken across the collector and the ground. This is the output, and this is the bypass circuit, this is a coupling capacitor, bypass capacitor, and this is coupling capacitor here. For this, if you draw the hybrid equivalent circuit, this is not the exact equivalent circuit. When you see the circuit itself, you can easily say that this is the approximate model because it has only 2 H parameters. The other 2 parameters are negligibly small, that is why we didn't include in the hybrid equivalent circuit. We know that this terminal is the base terminal, and here this one is the collector terminal, and here this is the emitter terminal because it is a common emitter configuration. It is not mentioned in the block diagram, but you have to mention everywhere where you are drawing this kind of circuit. This is the base, this is emitter, and this is collector. Here only the input impedance and the forward current transfer ratio is given, and this is, we know that this is an approximate model of the hybrid model of a transistor in common emitter configuration. So, this is HIE and HFE into IB, and you can ask that this is the current source and why it is HFE IB, and what is the relationship between these two HFE. We know that HFE is a forward current transfer ratio. Why not it is simply mentioned as HFE, why it is included with the IB? That may be your question. If you replace this HFE, what is the equation? If you replace this HFE, what is HFE first? It is a forward current transfer ratio. Forward current transfer ratio is output current divided by the input current, and what is the output current here? It is IC. Input current is IB. If you replace this HFE by IC by IB, the IB in the denominator you will be having IB in HFE term. So, IB and IB will be getting cancelled, only you have IC. Since it is an output side, this current source is an output side, this current is purely based on the output current IC. That is what you have to understood here. So, the input voltage is given across these two terminals Vi, and this R1 and R2 you have to connect this R1 from the input terminal to the common terminal, R2 is also connected to the input terminal to the output terminal. This R1 is connected between the supply and the base terminal, and R2 is from the base to the ground terminal. But when you consider for the hybrid model, this supply has to be grounded. That is the first consideration when you draw the hybrid model of any circuit. So, if it is considered as ground, then this R1 is connected from base to ground, this R2 is connected from base to ground. That is what here it is mentioned from, it is given from base to ground. R1 is from base to ground, R2 is also from base to ground. For any hybrid model, the supply is considered as ground terminal. That is what R1 is connected between the base and the ground. So, this is the circuit after replacing the hybrid model for the transistor. You got R1, you got R2, and you got this RE also. R1, R2 is given in the input side and RC is given in the output side. That RC is nothing but this, the load resistance, that is the resistance connected at the collector terminal between the collector terminal and the supply, but in this equivalent circuit it is from the collector terminal to the ground, since the supply is considered as ground. Let us have a break. Welcome back. So, we have seen the equivalent circuit of the transistor in voltage divided bias in a common emitter configuration. So, here voltage divided bias is through R1 and R2, it is connected between the input terminal and the output terminal, and the collector resistance is also connected between the output terminal to the common terminal. Here also it is connected between the input terminal to the common terminal. So, now for this circuit you have to calculate what are the parameters, that is H parameters. You know that this IB is the input current and this I0 is the output current here. Output impedance is simply here RC because HOE is negligible. If it is there, then you can give the parallel combination of RC and HOE, but do not bother about this HOE here. We are replacing the transistor with the approximate model. It is enough for the analysis. So, the Z0 value is only purely this resistance RC. And what is the voltage gain? The voltage gain is given as V0 by Vi, the output voltage by the input voltage, and V0 is given as the current into the resistance. This current, the product of the current and the resistance is the output voltage, but if you calculate the output voltage, the polarity is reversed. Here this current is away from this node. So, you have to include the negative sign in the equation, minus HFE IB, this is the current term, and this is the resistance RC, the current flowing through the resistance RC. So, this is the output voltage, and what is the input voltage? It is from the circuit, input voltage is IB into HIE. It is given Vi is equal to IB into HIE. If these two values are replaced for V0 and Vi in the equation AV, you will be getting, and IB cancelled. So, HFE RC by HIE. This is the voltage gain for this circuit. And what is the current gain? Current gain is I0 by II. I0, we know that this I0 is reverse in polarity. So, include a minus sign before HFE IB. This is I0. Here there is no negative sign, it is positive actually. I0 is equal to minus HFE. We know that I0 is reversed with this current source HFE. So, minus HFE IB, and IB, how will you write IB? IB is the input current which flows through the HIE parameter, and you have the resistance R1 and R2 here. If these two resistors are in parallel, then you can consider this parallel combination of R1 and R2 as RB. So, if the two resistors are connected and if you want to calculate the current through the resistance HIE, that is the input resistance, the current divider rule says that the input current into the opposite resistance divided by the total resistance. That is the current divider rule. So, input current is IB equal to II into the resistance, opposite resistance is RB. This RB is the parallel combination of the resistances R1 and R2. So, this is opposite to HIE. So, II is the source current, that is the current from the input side of the port. So, IIRB divided by the total resistances RB plus HIE, and I0 is equal to, instead of this IB, if you substitute this value, you will be getting II, that is the current amplification factor, as minus HFE RB by RB plus HIE. This is the final equation for the current gain or a current amplification factor. And next is multi-stage amplifier. Why we need to go with this multi-stage amplifier? Because in a single stage amplifier, that is if single transistor is present and if you give a very smaller amplitude signal is given to the input of that particular transistor, it amplifies and it produces some output, but in some cases the amplified output is not sufficient to drive any next stage. So, if you want to improve the amplified output of the transistor circuit or an amplifier circuit, you have to give the output of that circuit into the input as the input to the next stage. So, it amplifies. So, the output of that second stage will give you the sufficient magnitude signal to drive any device. So, in that case you are going with the multi-stage amplifier. If one output is not sufficient to drive a device, you are connecting another circuit to amplify that signal, or two or more amplifiers are connected in series to amplify the input signal of the first stage to higher value, so that it is sufficient to drive a device. That is why we are going with the multi-stage amplifier. So, this is the general block diagram of a multi-stage amplifier. Voltage source is given through the resistance Rs. This is the first stage. The output of the first stage is given as the input of the next stage, and after that you are taking the output through the resistance RL. So, here the two stage transistors are cascaded. Output of the first is given as the input of the next, then this particular connection is said to be cascade connection, two stage cascade amplifier here. This is source and this is load. This is a block diagram. This is the circuit diagram. Here there are three stages. This transistor holds the first stage. So, the output of the transistor across the collector terminal is taken as the input of the next stage. Input is the base terminal of the next transistor. So, the output at the collector of first transistor is given as the input to the base terminal of the second transistor. So, until here this is first stage, and here this is the second stage. So, again if the output of the second stage is not sufficient, the output of the second stage is given to the input to the base terminal of the next stage for the better amplification. So, here the output is given as the input, again the output is given as the input. So, this is in a cascaded connection. There are three stages here. This is the signal, and here you can take the output across the collector. Similarly, you can connect any number of stages. So, if the connected stage is two or more, then it is called as multi-stage amplifier. What are the types of coupling? In the sense, you have to connect the output of the first stage of amplifier to the input of the next stage amplifier. So, how will you connect the output as the input of the next stage? Through three types. One is RC coupling, next is transformer coupling, and the third is direct coupling. You can use resistance and a capacitance for coupling the output as an input of the next stage, that is said to be RC coupling. And also you can use a transformer coupling also. Instead of RC you can use a transformer, or you can directly connect the output to the input of the next stage. Resistance and the capacitance coupling, it is less expensive, frequency response is good, and coupling capacitor isolates the DC conditions of one stage from the next stage. This coupling capacitor, it will not allow the DC signal from one point to the other point. So, it is used here. So, it will not, the coupling capacitor isolates the DC conditions of one stage from the next stage. The transformer coupling, primary winding acts as a collector load. So, primary winding will be acting as a load for the first stage, and secondary winding transfers the AC output signal directly to the base of the next stage. So, secondary winding, it transfers the signal from the first stage to the base of the next stage. The circuit gain is high and it is expensive, so it is not normally used in all the amplifiers. It is only used, mostly used in the power amplifiers, large signal amplifiers otherwise. Next is frequency response of multi-stage amplifier. We have discussed about the frequency response of an amplifier when we are talking about the filters, or in the feedback amplifiers also we have discussed about the frequency response. What do you mean by frequency response is if the circuit, the performance of the circuit for the range of input signals frequency, the response of a circuit for a range of the input signals frequency. So, in x axis it is the range of frequency and in y axis it is the gain of the circuit. When you look at the graph, for the lower range of input signals frequency, the gain is slowly increased, and this is the mid-band frequency. This is the mid-band frequency. In mid-band frequency the gain is always constant as A, and the higher frequency the gain is reduced slowly, and this roll off is because of the capacitance effect and the circuit active devices in the circuit. These are the reasons for this roll off rate. When we are talking about the frequency response of the multi-stage amplifier, in the mid band has a constant gain as A, and for the lower frequency ranges the circuit will act as a high pass filter, and in the higher frequency ranges the circuit will act as a low pass filter. So, in the high pass filter we know that if you look at the path of this frequency response, then the frequency is, for the initial case the frequency is slowly increasing and it is constant, right. That is the frequency response of the high pass filter. High pass filter at low frequency range. If the frequency is very low, the effect of the circuit is a high pass filter. Why it is called as high pass filter also we have discussed in the filter concept. There is a relationship between the frequency and the capacitance, and it is inversely proportional. If the signal's frequency is very high, we are talking about the low frequency. So, if the frequency is low, what happens to the capacitance effect? It is very high, and this is open circuited and there is no connection between the input and the output. So, the output will be 0 for this circuit. So, this attenuates the lower frequency signals. So, at low frequency this attenuates the lower frequency signal, there will not be any output, and if it is a high frequency this will act as a short circuit because this value is very low. We are considering this as a short circuit, and so the output will be the whatever the input is given, the output will be taken across the terminals. So, this combination of R and C gives a high pass filter concept. At low frequencies we know that the output is nil, the output is 0. So, when you look at this frequency response at low frequency, the output is 0, it is ideally it is 0, but practically it will have some output. Ideal case it is given as a dotted line here. For the low frequency ideally it is 0, so there is no signal passed, but practically it has a slowly increasing gain, and after that, after the cutoff frequency, all the signals are passed through it. This is the response of the high pass filter, and at the response of the multi-stage amplifier also at low frequency ranges, and at the high frequency range the circuit will act as a low pass filter. For the low pass filter, what is the concept? If the frequency is low here, according to the relationship between the frequency and the capacitance, this capacitance is very high. If it is very high, you can consider this path as an open circuit, and the input voltage is always taken across the output. Whatever the input is given, if it is open circuited, the voltage will be taken at the output terminal. So, this will act as a low pass filter, allows only the lower frequency signals. What happens to the high frequency? If it is high frequency, it will short. So, across the short terminal, across the path, the output voltage, whatever the voltage, if you take the voltage across the short terminal, then the voltage is 0. If the line is shorter, then across it there is no voltage, that is the meaning. So, for the high frequency, it will not allow the frequency signal. So, that is what here. For the high frequency, when you see the dotted line, it is the cutoff frequency after which there is no signal passed through the amplifier, but practically the gain is reduced here. So, this is the frequency response of the multi-stage amplifier. To summarize this frequency response, mid-band the gain is A, and lower frequency ranges the gain is only 0.707 of the maximum gain, and here also after this cutoff the gain is reduced, and at this higher cutoff frequency, the gain is 0.707 of maximum value, and this is nothing but 3 dB value. So, this lower frequency range, the multi-stage amplifier will act as a high pass filter, and high frequency range will act as a low pass filter, and this is in general. We will see later the two coupling methods for the multi-stage amplifier. One is RC coupling method and next is transformer coupling method in the next session. Let us summarize today's topic. Single stage amplifier in common emitter configuration we have discussed, and the introduction about the multi-stage amplifier and what are the types of coupling methods and what is the frequency response of the multi-stage amplifier. There are some questions to check your knowledge. List the types of coupling method, derive the H parameters for CE with the voltage divider bias, discuss about the frequency response of multi-stage amplifier. These are the references. Thank you.